Hi everybody, Shushanik here with BikeOn. I wanted to make this video to give you some updates on what's going on with our company and with our product. So as you know, we are selling BikeOn. Many of you are our customers already and using it. We are constantly working on improving the product, and currently we are working on actually improving the torque sensor and replacing this roller torque sensor that we have now with a new torque sensor that will be like this. So this is actually something that goes on a chain, and it measures a lot of data. Not only limited data that our current sensor is measuring, but actually this will be a full power meter measuring different metrics. So you will be able to use this with BikeOn kit or as a standalone power meter by itself. So while we were developing this, we came to the conclusion that we can actually launch this as a separate product as well, not only together with BikeOn. So we are currently doing a pre-sale, pre-launch campaign before the crowdfunding that we are going to do for this product. And by the way, you can click the link in the description and reserve this power meter for the lowest price we will ever sell it for, which will be even lower than the one that will be doing crowdfunding. When we announced our new product, it happened just recently if you are following our social media, we have received a lot of questions, a lot of technical questions about how this power meter works. And Aram, as a technical co-founder, now will answer most of those questions. And if you have any more questions, please write them in the comment and we will be happy to answer them. Thank you very much.
Hi everybody, Aram is here, and I will answer your questions which you have so far regarding CycleClick. I will tell you how we designed it, why we designed it this way. We will also show you a comparison of the CycleClick data, one of the early prototypes of the CycleClick data with Favero Assioma Uno. There are several types of power meters. One of them is pedal-based power meter. You can see it on the other side. That's Favero Assioma power meter. The way those pedals they work, there is a very tiny small sensor glued onto the axle of the pedal, and that sensor is trying to detect very small deflections of the pedal axle. Those axles, they have to withstand your weight and then some more. That's why they are very strong. So to detect the small movements, you have to have very sensitive sensors, which means you will also detect a lot of noise and you have to deal with that. The second type of sensors is the crank-based sensors. Some sensors do the same thing but not on the pedal axle, they do it on the crank. Another one, another type, the same thing they do on the spider. It's all the same things. Again, spider, crank, pedal axle, these are load bearing parts. They have to withstand a lot of loads. Therefore, measuring those displacements and making a very high quality data might be tricky. The third type of sensors is hub sensors. I think it's less common nowadays, but the same sensors, they are built into the rear hub and they measure the displacement within the hub as well. Power flows actually from the pedal to the crank, spider, chain ring. Then it goes into the chain, the sprockets, and then hub, and finally it comes to the wheel. That's the power path. Anything we place in the power path, if we do it correctly, we'll be able to measure the power. The power is basically product of two measurements. First is the torque, second is the speed. So with this new sensor, what we have done, we wanted to avoid the limitation of building the strain gauges into a load-bearing part, which means that the strain gauge has to measure very tiny displacement. Here we got rid of that limitation, and here's how. We placed the sensor, we basically built a channel. You can see the channel here. It has two ridges. The chain passes through those ridges, and the rollers, they roll inside this channel. So there is no friction, but rolling action actually. And you can see very tiny hump. It's almost invisible here. That hump actually makes the rollers to press the bottom portion of the sensor. Here inside we have the strain gauges now, which measure the deflection of the bottom portion, and that gives us the torque, the tension of the chain. This little roller, it goes into the chain and it measures the speed of the chain. These are the two basic measurements which we make, and as you can see here, deflection of this lower part can be pretty large within what's called elastic deformation. And if the deflection is large, signal to noise ratio is very good, very good. We are able to measure very good data with very low noise, and that's one of the advantages here. Here, this plastic part is pre-installed. It's just one zip tie here, and here is a retention arm. There is a ball connection. I just push it in. The same connection exists here. So I'm going to push in the chain into this channel. It's not overly tight. I just pushed it in. You can see it moves without almost any detectable friction. I can actually do this and it will roll on the chain. Now I'm going to push in this portion here, and now the sensor is installed. There were some questions concerning about the vibration of the chain. Will it come off easily or not? It will not. That hump and the overall design of the sensor make it pretty robust. You cannot just remove it just by pushing it. There has to be some rolling motion which takes it out of the chain. You can see that no matter what I do, it's not that easy for the sensor to come off. It just sits on the chain. So the device becomes basically a part of the chain. You can see this ball connection of the retention arm allows the device to move with a chain, so that when you shift the gear with derailleur, it just moves this way. What constrains the device from moving back and forth is this connection here. So as I showed, it's very robust. One of the reasons why is it robust, because the device is very lightweight, and the force on the device because of vibration heavily dependent on the mass of the device. The lighter the device, the smaller those forces. That's one of the reasons why it's not so easy to come off because of vibrations. So I covered the fact that it basically is free to move with a chain this way. So if you shift the derailleur, it's going just to move with a chain, and we will show it again on a stationary bicycle. Derailleur position, does it affect the measurement? It does not. I just showed you that the device becomes basically a part of the chain. It moves with a chain except for back and forth movement. Some people actually asked to show what's going on with backpedaling. Here, just quick. You can see that it actually there is no resistance, or almost no resistance. So everything works like in your normal bicycle. Backpedaling is not a problem at all. Dirty chain on a rainy day doesn't matter. As I explained before, the deflection of the measuring part of the device is relatively large. So small particles or small dirt, first of all, the rollers, they kind of clean up themselves as they enter the device. And second, it doesn't really matter. We have tested the dirt, how it withstands the dirt. Maximum wattage. It can measure, we spec it up to 2000 watts. Base tension, does it interfere or not? Base tension of the chain, it does not. It's just too small, and it doesn't matter if the spring of your derailleur is heavier or lighter. It's just too small for the device to detect. That's one. It has auto calibration, actually auto zeroing option. Every once in a while it zeroes itself. It knows when to do it, so that the baseline is always there. So the base tension doesn't matter, base tension of the chain. Bouncing, yes, as I explained, it basically becomes part of the chain. It can bounce, but because it's so lightweight, the bouncing does not affect the measurements. It does not introduce any significant noise. So as I said before, the auto zeroing and constant auto zeroing of the device, it basically zeroes itself so that the chain wear does not affect the measurements. Besides, the wear is insignificant to the overall width of the channel, so it does not affect the precision. Some people say there are too many variables on a moving chain for this to be accurate. It depends on how you design it. As I explained, the device becomes part of the chain. It's very lightweight, and forces acting on the device are very small. So no, it does not, there is not too many variables. We measure the tension, we measure the speed of the chain. All the movement and all that, it's all accounted for. There is inner algorithm and computation which happening inside that device, so that's not a problem. How are we reading the cadence and other data? So it's a good question. As I said before, inside the device has a microcontroller which does all the computation. For example, the cadence, we measure the force on the device, and the peaks, or if we measure the force at some time and we detect the same level of the signal, we know that that's basically half of revolution of the pedals, because the pedal movement, it gives usually some sort of sine wave. So it's already baked in. Cadence measurement is not a problem. Shift the chain ring, we will do it now. Okay, so let me show you how it shifts. Again, I am going to install it. You can see I'm pushing it into the channel. It slides. I push the ball connection into the housing here. Now it's installed. And now the shifting part. That was the shifting. I'm shifting the gear back again and again. So shifting is not a problem. As I explained before, the device becomes kind of part of the chain. Not so easy to pull it off, not easy to come off. Shifting is not a problem. I know that some people express concern about the disturbance which device introduces to the system, about rolling resistance because the chain passes through the device. And I would like to address those concerns by showing, measuring, and explaining. So here's the device already installed on the chain. It rolls really freely. You can see if I just kick, it rolls almost by itself, it almost flies. But we want to measure it. Here's the force meter, and I'm now going to measure the force in newtons. I am going to apply tension as much as I can to the chain, and I'm going to try and roll the device. As you can see, we are measuring rolling resistance on average about 0.3 Newton. Is it a lot? How do we compare? What's the comparison here? So if you put out 80 watt, you use 175 millimeter crank arm. You use 32 teeth chain ring, which is pretty common setup. The chain tension is going to be about 200 newtons. Compared to that chain tension, the disturbance which this device introduces is about 0.15%. It's basically very close to 1/10 of the percent. The precision and spec of this device is plus minus 1%. So we are talking about tiny, minuscule part of the disturbance which the device introduces. So in short, the device does introduce some disturbance, but it's very, very small, which does not affect the precision or does not affect your feel as you pedal. Another thing I wanted to address is the design itself. People think that this hump which we have here, it's a huge hump, and as the chain rolls through it, it creates the hump itself, creates a lot of resistance. I would like to clarify. In this design, unlike other conventional designs, we have many levers to pull in order to optimize the system. For example, the metal part here, which basically deflects, and we measure that deflection with strain gauges, it can be thinner, it can be thicker, the hump can be higher, it can be smaller, the electronic sensitivity inside the device it can be higher, it can be lower. There are many levers which allow us to make this device very precise and very efficient. So here is comparison, one of the early runs of CycleClick compared to Favero Assioma Uno. And first thing we can notice here that Favero has about 90 data points. CycleClick has over 3,000 data points here. And we can see a very good correlation of the data. The blue is CycleClick, orange is Favero Assioma, and you can see that the power levels are pretty low, 120 watts at peak and lower. It's done intentionally because it's harder to detect lower power precisely than higher power. You can see the data comparison again. Blue is CycleClick, orange is Favero Assioma Uno. If you have any more questions, please let us know in the comments below. Thank you very much for your time. As Shushanik mentioned, we are preparing a crowdfunding campaign for the sensor product. If you are interested, click on the link below, visit our pre-launch page. You will be able to reserve the device for half the price, lowest price ever. And again, if you have any questions, please let us know. Thank you very much.